Hello, it's Stat 135, Lecture 30. Last time we started ANOVA, analysis of variance, to test the null that the differential effect alpha I for each treatment group is 0. This is equivalent to all the groups having the same mean. So this is a generalization of the t-test, which is two treatment groups, or a treatment group and a control. We saw the equality SST is SSW plus SSB. The sum of squares total is the sum of squares within plus the sum of squares between. In the case of an example, the general proof is on page 480 in the book and is just an algebraic proof that I'm not going to go over. What I want to concentrate on is showing you why these divided by sigma squared is a chi-squared of various degrees of freedom. So last time we showed that SST over sigma squared is a chi-squared with ij minus 1 degrees of freedom. We also showed that SSW and SSB are independent random variables. So today we're going to show that SSW and SSB over sigma squared are chi-squares, and we'll review the F distribution and F test, and then we'll introduce the Bonferroni method for multiple comparisons. So the example we were looking at last time was a 3 by 3. I've taken a transpose of this picture here, putting the labs I as the rows and the observations J as columns. And we have row means 2, 4, and 6, and the total mean is 4. The SSW, we can then compute these 9 terms here, give you 6, and we realize that each of these groups of 3 is in fact a multiple of a sample variance. The sample variance for group A, sample variance for group B, sample variance for group 3C, so all multiplied by j minus 1. And we can introduce the pooled sample variance, which is the average of these 3 sample variances, and we can write it by multiplying the top and bottom by j minus 1, and so we see that the pooled sample variance is the SSW over I j minus 1, and so we have here the degrees of freedom times the sample variance over sigma squared. This is a chi-squared with I j minus 1 degrees of freedom. And so we say that SSW is a chi-squared with I j minus 1 degrees of freedom. On to SSB. So for SSB, which is the spread of values of the row means about the total mean. So here we get 9 terms again, but we have essentially j times just 3 terms. We get 24 in this case. And just noticing that in this example, SST is 30. We saw last time SSW is 6. We just saw, and SSB is 24. So that makes sense. Equality, again, is shown generally on page 480. So now to determine that SSB is a chi-squared, we're going to use various facts. So 1, this equality. 2, that SSW and SSB are independent. and 3, the chi-square subtraction property, which says that if x is a sum of two random variables that are independent, and x is a chi-squared with n1 plus n2 degrees of freedom, and x1 is a chi-squared with n1 degrees of freedom, then x2 is a chi-squared with n2 degrees of freedom. The proof of this is a very simple moment-generating function argument, but I'm going to skip it. So here we have n1 is the degrees of freedom of SSW, which is I, j minus 1, and n1 plus n2 is the degrees of freedom of SST, which is I, j minus 1. And so n2 then is the difference of these, which is just I minus 1. So we say that SSB has I minus 1 degrees of freedom, or is a chi-squared with I minus 1 degrees of freedom. So in this example, you can see the equality of the degrees of freedom as well. So now we can do an F-test, which is so the F-test is a test statistic. F is a test statistic, which is a ratio of two chi-squares divided by their degrees of freedom. So we have SSB over sigma squared over I minus 1, SSW over sigma squared divided by I, j minus 1. And so in our example, we get 24 over 2 divided by 6 over 6, which is 12. We can compute the p-value of this. This is a one-sided test. So it's 1 minus PF 1226. That's 0.008. So we would reject that all the treatments have the same mean, let's say with alpha is 0.05. So the assumptions in this model, the normal theory F-test has several assumptions. Our data is normal. The variance of each treatment group is the same, and all observations are independent. If you don't satisfy these assumptions, you would do a non-parametric Kruskal-Wallis test, which we'll do next time. So in the previous example, we rejected the null, but we don't know which differential effect is not the true mean. So in other words, we don't know which pairs are significantly different. And so for this, we do a Bonferroni method. And so the idea here is that we're going to do multiple comparisons. So doing an F-test and rejecting the null allows us to conclude that at least one of these alpha i's aren't zero, or equivalently not all the groups have the same mean. However, it doesn't tell us which group has non-zero alpha I, or equivalently which two groups have different means. So let's say that n is the number of treatment groups. That was what we were calling I before. So we're going to make n choose two simultaneous confidence intervals. Okay, so we're going to do all these simultaneous confidence intervals. It's n choose two because these are all the pairs of groups that we can choose. And we're going to do, so we're going to form these confidence intervals, which is equivalent under duality to basically hypothesis testing, in other words, t-tests. So now the confidence interval corresponds to a t-test that the two groups have the same mean. In other words, the difference of their means is zero. So the chance that at least one of these confidence intervals doesn't contain zero is less than or equal to alpha, right? That's what we want. So you can just think of if you were to do many t-tests, right? If you were to do that many t-tests, so it's likely that one of them, at least one of them, you would end up rejecting the null, right? So we got to make it harder to reject the null. So we're going to make the significance level for each hypothesis, for each t-test, we got to make the significance level harder or smaller. And So that's what we're going to do now. So here's some details for you. So let Aij be the event that groups I and j don't have the same mean if the null is true, right? So so the union of these Aij's is the event that at least one of the pairs of groups have different means, right? And assuming the null is true, the error in this probability, we need to control it to be less than or equal to alpha. So like I said, we're performing many pairwise t-tests, and so we're going to have to make it harder to reject each t-test. So how much harder? So what we're going to do is we're going to change the level significance for each individual t-test from alpha to alpha over n choose 2. And to see why, we just have the addition rule. The probability of this union of Aij's is less than or equal to the sum of the p Aij's. So the probability of Aij is, so given the null, that is your level of significance. So that we need the probability of Aij to be alpha over n choose 2, because we're looking at a sum here of n choose 2 terms, each with an error. So we need the error to be alpha over n choose 2 so that the sum will just be alpha. So for example, for I is 7 treatment groups, this means doing 7 choose 2 or 21 pairwise t-tests with significance level alpha over 21. Wow, 21 pairwise t-tests, that's a lot of work. Well, we'll do that next time, so I'll see you on Friday.